The last talk is Joaquín Soriano. Joaquín Soriano is also in Valencia. He is coming, initially he was in the group of José Ramón Galán in Tarragona, in the ISIC. He was working there with polyoxometalate chemistry, and using polyoxometalates, he was trying during his PhD to make systems interesting for electrocatalysis, interesting for water splitting. And then what he is going to show you today is some introduction to this water oxidation catalysis that you can have with polyoxometalates. Then you have had already 2 or 3 talks about energy, and then this is about batteries, for example, yesterday, about some hydrogen, obtention of hydrogen from electrocatalysis, and today is a talk in which he's using, in that case, polyoxometalate chemistry to develop also electrocatalysis. Then.
Thank you, Kenny. I was going to say good morning, but actually it's afternoon. I'll try to be fast because I'm really starving, so I don't want to pass out here. So today I'm going to talk about water as an energy vector, and mostly about water oxidation catalysis. So I will start with an introduction about the importance of water oxidation catalysis, and then I will show you a couple of examples about using polyoxometalates as catalyst for the process. So as you know, our society relies strongly on the use of on the combustion of fossil fuels for energy production, where the use of renewable energies and nuclear power remains in a very small portion of the total. So the first thing we have to ask ourselves is why fossil fuels are so important, and why our society is based on these fossil fuels. So this is because they are very abundant. They give us a high energy and power density. They are chemically stable. They are easy to store and transport, and the most important, they are really cheap. So we have to take this into account in order to change to something more renewable. But as you know, the problem with fossil fuels is that they lead to CO2 emissions into the atmosphere, and because of the absence of natural mechanisms of atmospheric CO2 destruction, all the CO2 that we accumulate there for the next years will remain there for several centuries. So this, of course, is causing global warming and climate change. So we need to move through a carbon-free energy source, where the most reliable is solar energy, and we have to harvest this energy, and then we have to store it. And one of the forms to do this is to store it into chemical bonds between a 2-electron bond between lighter elements. And we can do so between in the form of hydrogen, or in the form of nitrogen-based fuels like ammonia, or in the form of hydrocarbon fuels like methane or methanol or whatever. So the most interesting for us is hydrogen, because they give us the largest energy by density mass, although it has a drawback that it is a gas. So in order to do so, we first need to understand natural photosynthesis. And in this process, this is driven by light, where water is oxidized to oxygen, and the protons and electrons produced there are used to reduce CO2 to sugars. So this reaction starts in the photosystem 2, and specifically the oxygen evolution reaction occurs in this oxygen evolving complex, which is a manganese cuban cluster. So this is the key reaction for the artificial photosynthesis. So this reaction is called the water splitting reaction, in which 2 molecules of water are oxidized to oxygen, and then the protons and the electrons are reduced to hydrogen. So this reaction can be divided into some reactions. One is known as the oxygen evolution reaction, or water oxidation. And then the second one is the hydrogen evolution reaction, or proton evolution. So of these 2 reactions, the bottleneck reaction is considered to be the oxygen evolution reaction, because it's a very endergonic reaction. And in addition to the thermodynamic potential of water, we need to apply more energy in order to overcome the activation barrier, concentration effects, and ohmic drop. So to this extra energy, it's known as an overpotential, and it's basically the extra energy we have to apply when we subtract the thermodynamic value. And in order to reduce as much as possible this overpotential, we need to use a catalyst. An ideal catalyst would be one that gives efficient oxygen conversion at 0 overpotential, delivering high current densities. It's based on inexpensive materials. It possesses long-term stability under strong oxidation conditions and preferably under acidic conditions. And of course, it has to work under heterogeneous conditions to be applied for industrial processes. Let me show you some molecular water oxidation catalysts. In this catalyst, we have a metal ion, which is basically stabilized by an organic ligand. And so they are pretty good evolving fast oxygen evolution kinetics. They are well-defined structures as they are molecules, so they are very easy to characterize, and they allow us to study the reaction of mechanisms. And they are very, of course, easy to tune and process. But they have many drawbacks because the most active catalysts in these conditions, they are made out of ruthenium, so it's an expensive metal. And because they have organic ligands, they don't survive very long under oxidative conditions. And this produces a metal leaching into the system, so you are applying oxidative potential. This, when you have metal ions in solution, you will create an oxide layer on the electrode. And basically, this will preclude the identification of the true catalyst, because this metal oxide will be also pretty active under these conditions. So in order to overcome some of these drawbacks, there are some methods to heterogenize these molecular catalysts on the surface of a support, and there are different methods, but still some of them are very expensive, and long-term stability is an issue. So regarding heterogeneous conditions, we have, this is basically the most interesting are metal oxides, like layer double hydroxides, double peroxides, spinels. And we also have other type of heterogeneous catalysts that are not oxides, such as Prussian blue analogs, metal organic frameworks, or single atom materials. The problem with these materials is that as they are heterogeneous materials, they are more difficult to characterize and to process, but they have a very good stability under most of the conditions we use. So now let me talk to you about some of the devices that are being commercialized, so that we can differentiate here between two kinds of devices. One works under basic conditions and the other works under acidic conditions. So the alkaline electrolyzer uses an aqueous electrolyte, in this case, very basic conditions. And we have the cathode and the anode are separated by a membrane that transport the hydroxyls that are produced on the cathode. And in the case of the acidic electrolyzer is a proton exchange membrane electrolyzer, which uses a solid state electrolyte that transports the protons that are produced in the anode through the cathode. And this creates a local concentration of protons that in the surface of the electrode. So regarding the catalysts that are used in these systems, in the alkaline electrolyzer, they are mainly used third-row transition metal oxides because they are very stable under basic conditions. And as you can see, some of them work really well, so they are very easy to implement. On the contrary, with the PEM electrolyzers, only iridium and ruthenium-based materials can be employed because they show relatively long stability under these strong acidic conditions. But they have some advantages and disadvantages, but the main problem here is the cost for producing hydrogen, which basically we cannot compete with fossil fuels for hydrogen production. So we would need to reduce around 1 order of magnitude the price of the hydrogen. And in addition, a real breakthrough with this technology would come if we were able to produce catalysts that are based on earth-abundant materials that can be applied with proton exchange membrane electrolyzers, because they present more advantages than the basic working under basic conditions. So now let me show you about the reaction mechanism. So I'm showing you here the reaction again, in which we have 2 water molecules that produce 1 molecule of oxygen for protons and 4 electrons. But it seems quite a straightforward reaction, but is it actually a trivial reaction? Well, no, it's not. Because basically every single catalyst might follow a different reaction mechanism, and this is a mess. So lucky for us, this can be kind of reduced to 3 general reaction mechanisms that most of the catalysts might follow with some small variations. So the first reaction mechanism, it's known as the water nucleophilic attack, in which we start with the metal of the active site, in which water binds to the metal, and after one oxidation, in which we lose a proton and electron, we obtain the hydroxyl species. After a second oxidation, we have the oxo species, and this is known as the active species because the water will nucleophilically attack to this oxygen to form the oxygen-oxygen bond. Then we end up with a hydroperoxide species, and after another oxidation, we evolve oxygen and we recover the catalyst. So the second reaction mechanism is known as the interaction of 2 metal oxo units. Basically, the first 2 steps are the same until we reach into this scenario where we have 2 metal oxo species near side. These 2 oxygens will interact to form a peroxo unit, and then oxygen evolves from this species, and we recover the catalyst again. And the third reaction mechanism is known as the lattice oxygen mechanism. This was proposed like a few years ago, and this has only seen under acidic conditions. And basically, the 2 first steps are the same, but in this case, the oxygen bond formation comes from a lattice oxygen from the metal oxide, and this forms the oxygen, and oxygen evolves, and leaving this vacancy here. So this might lead to a way to the activation of the metal. So we can recover this vacancy by the introduction of another water, and it's oxidized. So we have this hydroxyl species here, and after the last oxidation, we can recover the catalyst. So now I'm going to talk about polyoxometalates. So you might know by now what a polyoxometalate is. It's a discrete anionic cluster made of early transition metal oxide building blocks on their highest oxidation state. And I'm presenting here what is called the Keggin moiety or the Keggin archetype. In this Keggin archetype, we have 12 metal atoms. In this case, they are tungsten, which are placed in the center of this octahedra. In the vertex of the octahedra are placed the oxygens. And then we have an heteroatom, which in this case is phosphorus, and is shown here as a tetrahedral in orange. So they are interesting because if we put this in solution, we will have very acidic solution. And if we increase the pH, we can remove some of these tungsten, octahedral tungsten, to have these lacunary species. And they are interesting because they are all inorganic multidentate ligands that can be used to stabilize transition metal oxide clusters. So, and also they have very interesting properties because they are very, very stable under harsh conditions, and they have very rich electrochemistry. And also they possess the stability of the heterogeneous catalyst with the tunability and processing of homogeneous catalysts. So they are very interesting to be used as a catalyst under oxidation conditions. I want you to see on this particular lacunary species because the polyoxometalates I've been used on are based on these species here. So I've been working with these 2 polyoxometalates and some variation of them. So this first one is known as the cobalt-9. And in this structure, we have 3 lacunary Keggin units that are encapsulating a cluster of cobalt oxide, which has 9 cobalt atoms. And they are also held by 2 phosphate units in the center and they present 6 molecules of water binder to the molecule. The second polyoxometalate is known as cobalt-4, and it presents what is known as a weakly sandwich because 2 trilacunary Keggin units are sandwiching a cluster of tetraoxo core of cobalt, and we have 2 molecules of water in its external side of the polyoxometalate. So now I'm going to start with examples. In this first example, we took the cobalt-9 in the solid state, and we tested the catalytic activity under acidic conditions. So for doing that, we put this in solution, and we basically obtain the insoluble salt just by metathesis. So we got either cesium or barium, and here you can see some images. The cesium salt is a bit more crystalline than the barium. So we took these salts and we prepare modified carbon paste electrodes. Carbon paste is basically amorphous carbon with some inorganic binder, and it serves as a support for these solid state polyoxometalates, and also to increase the conductivity because polyoxometalates are quite insulators. So for doing this, we mix the polyoxometalate and the carbon paste in a mortar, so that we have a homogeneous blend, and we will introduce this blend inside the pocket of the electrode. So we have our electrode ready, and in this case, we use 1 molar sulfuric acid as electrolyte, which gives us a pH around 0.1, 0.3. So first thing we did was a linear sweep voltammetry. And a linear sweep voltammetry, we increase the potential and we measure the current intensity we obtain. So here, as we increase the potential, we see an increase on the values of the intensity. And that means we have a multi-electronic process. And in this case, it's a catalytic process, which is water oxidation for us. So here we can see that increasing the amount of the catalyst inside the blends of the modified carbon paste electrodes, we increase the catalytic activity, and we compare the cesium salt with the barium salt, and we were quite surprised to see the barium salt gave a really good onset over potential, which is the potential in which we start the reaction. And so we were actually surprised to see that the barium was much better than the cesium. And also it gives an 88 millivolts over potential, which at that time was the lowest over potential reported. And I think is one of the lowest reported right now in acidic conditions. So we were very happy with that, but first we wanted to compare it with iridium oxide because it's basically the benchmark catalyst and in the acidic conditions. So we took commercial iridium oxide, we prepared the same carbon paste blends, and we compared the activity with this cobalt-9 polyoxometalate. And we can see that even for a 40% of iridium oxide inside the blend, this cannot match the activity with the polyoxometalates. So we were pretty happy, but not happy enough because these polyoxometalates, under certain conditions, they can leach cobalt on the solution. And this cobalt, as I said before, if you leach metals there under oxidative conditions, you can form an oxide. So we could be forming cobalt oxide and could be the active species under this condition. So we also compare it with cobalt oxide. And we can see here that cobalt oxide was also quite active, but it couldn't match the activity of the cobalt-9. And just to you to know, 40% of cobalt oxide possess many more atoms of cobalt than 40% of cobalt-9. So we would need a huge amount of cobalt-9 to be converted into cobalt oxide to have this activity. But I will show you more proof that we are not forming cobalt oxide under these conditions. But still, cobalt oxide was pretty active here under these conditions, and it was like blowing our minds because cobalt oxide should not be stable under pH 0, and even the cobalt-9 should not be stable under these acidic conditions. Actually, we took cobalt-9, put it under 1 molar solution of the sulfuric acid, and basically what you get is a precipitate, is a white powder, which is the plenary Keggin atom, and you have the cobalt ions in solution. So this was telling us that the carbon paste was not innocent under these conditions because it was creating a hydrophobic environment around the polyoxometalate that was protecting the polyoxometalate. So we said that we continue with our study. So in order to have a more fair comparison with these metals, we also compare the activity, taking into account the amount of metals we were having in each blend. So here we can see that the barium and the cesium salts of the cobalt-9 were much more active than iridium and cobalt oxide. So we also compare the activities of these electrodes using a Tafel plot. In a Tafel plot, this comes from Tafel equations that the air, so you will measure the change of the current density in front of the overpotential. And basically, this is a very strong tool for comparing the electrocatalysts. So basically, you will have a straight line coming from the beginning of the catalytic reaction. And from this slope of the straight line, you will have information about the kinetics of the reaction, and also will tell you the mechanism, some of the mechanism of the reaction that the catalysts are following. So I don't know if you can see it here, but both catalysts, both cobalt-9 electrodes showed a very similar slope. And the cobalt oxides show a much higher slope, which is typical for cobalt oxide. So this is another proof that we are not having cobalt oxide in our electrode. And we also compare it with the iridium oxide, which gave us typical values for iridium oxide. So we can see here that again, that the barium salt of the cobalt-9 was even better than the most active material based on iridium that was reported at that time, at least for low overpotentials. So then we measure the oxygen directly from this cell. So this is an H tube in which we have the anode and the cathode separated by the porous frit in order to avoid the cross of the gases and the recombination of the gases, and this should be very tight. And I really hate these measurements because they are a real nightmare. So yeah, we cried a lot during these measurements. And so we run a chronopotentiometry in which basically we apply a current density and we measure the variation of the overpotential with time. So we measure the oxygen evolution and we can see that it's Faraday. Faraday means that if you compare it with the theoretical amount of oxygen that you produce, we obtain around almost 100% of the oxygen evolution. So also we have here a delay on the measurement because this is a porous material, so the oxygen bubbles would stay here for a bit, and it takes a time until they reach the gas space in which we have the oxygen sensor. Also, we measure the oxygen evolution with the cobalt oxide, and here we can see that it is not a Faraday reaction, and that's probably because the cobalt oxide is also catalyzing the oxidation of the carbon paste. Then we recover the catalyst and we characterize it. Infrared is very powerful with polyoxometalates because every polyoxometalate will have a fingerprint, a distinct fingerprint. So here we can see that before and after the catalyst remains almost the same. Also, Raman is very interesting for us because with Raman we can see if we have any oxide formation. And here we can see the before and after, they are the same. And also if we compare it with the cobalt oxide, we see that there is no trace of cobalt oxide. And finally, also XPS, again, is very useful for identifying the oxide formation. And here we can see that the polyoxometalate is the same. And also we don't have any oxygen value coming from a lattice oxygen, which should appear below 530 EVs. So, well, we also studied the long-term stability of these polyoxometalates under these conditions, and we can see that they are perfectly stable for at least 24 hours. And we, again, compare it with other catalysts. So we can see they are more active under these conditions than iridium oxide and cobalt oxide. And we also compare it with the copy catalyst. There's no copy catalyst or Nocera catalyst, which is analogous to cobalt oxide, which is probably the most active material under neutral conditions. And we can see it was pretty active for the first 8 hours, but then it slowly decomposes. And we also compare it with the spinel, nickel iron spinel, which is one of the most active materials under basic conditions. And yeah, basically it was stable as well, but not so active. And also if we compare the activity, taking into account the moles of metals that we use in each electrode, we can see that none of them could match the activity of the barium cobalt-9. And also we estimated the turnover numbers, and we can see that, yeah, again, the barium cobalt-9, has superior performance than any other catalyst. So now I'm gonna show you the second example here, and this is regarding about the fine-tuning of polyoxometalates to increase the activity. So in this case, we took this cobalt-4 structure, and the idea was to introduce some molybdenum atoms to replace some tungsten into the addenda atoms. This is known as addenda atoms. So for doing this, the idea was to take the synthesis of the cobalt-4 and replace some of the tungsten by molybdenum with different synthetic ratios. And we were lucky to obtain reproducible results with 3 different ratios. So as we can see that when we increase the amount of molybdenum into the synthesis, we could also increase the amount of molybdenum in the crystal structure. And also we got from each synthesis, we got 2 different polymorphs, and so we end up with 6 different crystals, and we studied the structure of all of them. So here in this picture, I'm showing you the tungsten occupancy across the structure. So these squares here belong to this different position of the addenda atoms. And as you can see here, the tungsten has some preferential sites here in these positions. And when we move through the structure of the polyoxometalate to these positions, so we start finding more amount of molybdenum. So basically all crystals type A and B preserve the tungsten to molybdenum ratio. So from each synthesis, we have 2 different crystals that they present the same tungsten to molybdenum ratio, and the only difference is a slight variation of the countercations because we use sodium and potassium as countercations. So we took these 6 crystals, we precipitate the cesium salt of the crystals, and we run again more water oxidation tests. This time they were under neutral conditions. And first thing we did was a linear subvoltammetry, and we can see here that when we compare it with the parent cobalt-4 with no molybdenum into the structure, we can see that in both cases, increasing the amount of molybdenum in the crystal structure would increase the catalytic activity. So we could increase reduce the onset potential by 180 millivolts. And then we also tested the long-term stability of the most active crystals. We see that they are perfectly stable under these conditions. And we also measure the oxygen evolved. We again obtain Faraday efficiencies. So yeah, we were happy with that. And yeah, I have finished. So as a conclusions, I hope I show you that water oxidation catalysis is key for the development of and deployment of renewable energy technologies, and the oxygen evolution in strong acidic conditions with earth abundant catalysis, a current major technological challenge. Also that barium salt of cobalt-9 shows unparalleled performance in acidic media, and also that's important because this will help to develop more catalysts that would not be otherwise stable in the acidic conditions. So if we tune the hydrophilic character of our composite electrodes, it might open to new opportunities to develop this low cost acid water electrolysis. And also finally that incorporating molybdenum into the structure would increase the catalytic activity. And this also show us that we can do bottom-up rational design of our catalyst to increase the catalytic activity. So yeah, I want to thank all the people involved in these projects, also the funding bodies, and all of you for your kind attention.
Then thanks, Chimo, for the talk about polyoxometalates in electrocatalysis. Then now we are going to have time for some questions. Yes, Alicia?
Thanks, Chimo, for the talk and all the explanation about how it works, because it was really, really nice. And I have a curiosity because you study a lot of different things, but you didn't play with the blending, the carbon matrix that you use, no? Or you,
No,
but
that was a commercial one.
okay, but this could be important. In the conclusions, you say that getting different, for example, hydrophobicity, it can be really good. So this can play an important role also in the performance, no? Playing with different, like with people that use carbon nanotubes or 2D materials or this.
Yeah, I'm actually working on that right now.
Okay.
Yeah, to move to some other carbon materials that could be applied to PEM electrolyzers. Because this carbon paste, it's okay for testing in the lab, but it's mechanically unstable, so you cannot put it into a PEM electrolyzer. Because basically it breaks down. It's not stable there.
Thanks.
Any other question? Yeah.
Thank you for the nice talk. I have a question about your cobalt-9 POM. Have you tried the catalytic activity in basic medium for this compound?
No, not in basic.
Okay.
Only neutral media and acidic media.
Okay, so
Yeah,
only in.
We were interested in acidic media because
Okay.
basic media, there are many catalysts already that work really well. So.
Okay. And concerning this, when you replace the tungsten by molybdenum, so how did you do it? Did you do in situ? You took cobalt-4 POM and then you added molybdenum?
No. We started with so we took the synthesis of the cobalt-4. Basically, it's just a one-pot reaction. So we took the number of moles of tungsten that we were employing for the cobalt-4. So we changed the ratio tungsten to molybdenum, and we end up with the same amount of moles of metals, molybdenum and tungsten.
Okay.
So it's a one-pot reaction.
Okay. And also it was possible to define the position of molybdenum in the crystal structure? Like it's a bit hard to differentiate.
It was really hard. So actually they are like a blend of different polyoxometalates with a final ratio of, with different final ratio, for example, this one to 11. But we observed with mass spectroscopy that it was like a range of different polyoxometalates with this final ratio.
Okay.
But they were consistent for this during when we repeated the synthesis. We could also identify in solution the structure with 18 molybdenum and no tungsten, but we couldn't crystallize this.
Okay, thank you. Can I ask you another question?
Okay.
Okay. And what about photocatalytic activity? If it is electrocatalyst, can it be also a photocatalytic catalyst?
We have tested also under photo-induced oxidation condition. Yeah, it also produces oxygen under solid state and also in the homogeneous phase.
Okay, we have two questions from the chat. Now we start to complicate also with chat. It's fine. Then the first one is if in this cobalt polyisotope states you have cobalt as active site or also tungsten?
It's only cobalt.
Only cobalt is the answer. Okay, and then there is another question. Well, the question is to compare the catalytic activities of cobalt-9 with cobalt-4. How would they compare both?
Cobalt-9 is more active than cobalt-4.
Cobalt-9 is more active than cobalt-4. Then and then the other thing that he's asking is, or Mario is asking also that why in that case cobalt and not iron or nickel are used?
Yeah, we have tested the activity of this weekly sandwich with manganese, but manganese is not stable. We have tested with iron. Iron is a bit less active than cobalt, but of course, iron is more interesting from a point of view of it's more there is more iron in the crust. So yeah, it's also active, but not as active as the cobalt one. And somebody else tested with nickel, but it's not active.
Okay, then, well, you have already answered to all the questions, because the first question of Joaquín, well, Mario, Joaquín is you, of Mario is well, he was confused about if it was the POM cluster or the cobalt that were active, and you respond that was more the cobalt, then in that case, there is no problem. Okay, then I think that all the answers are, well, he's answering, thanks, then no problem. You approved the exam now. Then you can pass to the next step. You can, during the lunch, he's out here to give a talk during 3 hours about this topic. Then you don't need to.
Can I have one?
And then by streaming, then these people will be connected, that you can continue talking about the use of polyoxometalates in electrocatalysis.
Bring me a tupper.
Okay, then I bring you something with marisco.
Oh, no, please.
Okay, then thank you very much to everybody. Then we go to lunch.